Okay, so let me introduce the speaker for the seminar today. So Jan is a senior data scientist and the principal investigator in the Physics and Computational Sciences Division at Pacific Northwest National Laboratory. Jan is an expert for SciML, and his current research is focused on differentiable programming for scientific machine learning, constraint optimization, and model-based optimal control with applications in the energy sector, including building control and power systems optimizations. Today, he's going to talk about differentiable programming for modeling and control of dynamical system. So we look forward to your talk. Yeah.
Thank you very much, Son, for introduction, and thanks, Ben, for the invitation. This work is in collaboration with many of my wonderful colleagues at Pacific Northwest National Laboratory, and I will quickly skim through the names. It's Aaron Tuor, Shriyank Abhyankar, Ethan King, James Koch, Zhao Chen, Soumya Vashist, Vikas Chandan, Vences Cortez, Shayag Mukherjee, Mahantesh Halappanavar, and Drgona Vrabje. So as you can see, we have a large group of people, all with different backgrounds from control theory, constraint optimization, dynamical systems, power systems, and aerospace that are combining their expertise for main purpose of modeling dynamic systems. Simulations are crucial for many areas of decision-making and scientific discovery. That's why we are dealing with them, but there is an accurate need for improving the computational efficiency and scalability for heterogeneous scientific simulations. And recent approaches are combining classical numerical methods, physics-based models, with neural networks. And there have been a lot of headlines how neural networks can solve largest or solve difficult problems like PDs, ODs in the context of scientific computing. So at the lab, we embark on this trend, and we are implementing these methods and doing research in their theoretical properties as well as implementation in software. Applications, as Son already mentioned, we are primarily dealing with energy systems. We are Department of Energy National Lab, and we have buildings, we have power systems, we have unmanned vehicles, we have molecular dynamic systems, anything that can deal with energy efficiency and energy applications. But once we have these dynamical system models that can represent complex systems, how do we do control with them? Because very often we want to change the parameters and see how the system responds. And we want to see the optimal response that minimizes the energy, satisfies thermal comfort, stabilizes the grid, balances the grid with supply and demand. There are in general two approaches for doing control. One is model-based, and the flagship of model-based approaches for decades has been model predictive control. There is also a famous statement, I think it was from Richard Murray from Caltech, from his textbook, that 95% of industrial control applications are PID loops, proportional integrated derivative controllers, which are very simple, that can be designed just with 3 parameters, and the rest is model predictive control. It has been popular mainly in process control industries, aerospace, automotive, and high-performance robotics, primarily because you have available differential equations that describe these processes. You can implement them relatively accurately. And once you have these accurate models, you can construct constraint optimization problems that solve optimal control problem. However, what happens when you don't have expensive PhD students or whole control teams that can describe your system dynamics model? What happens if your system is too complex to be described by a set of differential equations? Then you can use reinforcement learning, where it was successful mainly in the domains where you have reliable digital twin model. It doesn't need to have any properties like differentiability, or doesn't need to be lower order. It can be really any computational system. And it has mostly discrete action space, although like continuous action space reinforcement learning has been also implemented. And you can use massive amount of compute to solve the problem. So you are doing primarily trial and error on this simulation environment. You are observing the response, through the reward signal, and then you are constructing the approximation of the behavior of the system through value functions. Both approaches have pros and cons. With model predictive control, you need to have a reliable system dynamics model that is very costly to obtain. Sometimes we don't even know the physics. With reinforcement learning, you can learn the policies with any simulation model, but requires large amount of compute, and very often you cannot satisfy stability or constraints or some performance guarantees as you would have in model-based approaches. In both of the communities, the trend is to come in the middle and develop hybrid methods that leverage benefits of the both, robustness of model predictive control and flexibility of reinforcement learning. We have similar tasks, but before we do so, we want to step back and see how the optimization is being done in each of those domains. Classical model predictive control is solved through online optimization. You formulate or reformulate your problem in nonlinear objective, equality, inequality constraints, and for a given measurement of your parameters that can represent your initial conditions, boundary conditions, or control objectives, you are obtaining single solution, control decision actions, with iterative solvers like interior, point, or active set methods. This works very well. It's a perfect solution when you have the model and when you can afford the compute in real time. It has been implemented in many systems, like in automotive, in process control. It's basically working 24/7. But what happens when you don't have the compute, and what happens when you cannot afford expensive like FPGAs, let's say, to deploy on a platform? People have been looking at what is called parametric programming, which deals with pre-computing explicit policies or solution maps for the optimal control problem with the use of analytical methods. The idea is wonderful because instead of solving the problem in real time, you just pre-compute the problem offline, and then you just see the solution from the lookup table or from the memory that can be approximated by some piecewise FI function. The classical methods, however, for these approaches, they don't scale. So unfortunately, it hasn't been proven to be practical for large-scale applications or for systems of larger state spaces. Recently, people have been using imitation learning to solve the problem. How? Well, you have labeled data set of your control parameters and optimal decision variables that you either obtain from the expert, like human driver, or you obtain from optimal controller that has been solved with iterative solver. And then you have sufficiently large data set that covers the parametric space you are interested in, and then you do simple regression or classification problem on this labeled data set. That's classical machine learning that has been working perfectly for decades on these type of tasks. This is again offline optimization because you obtain the explicit representation of your control policy approximated by, let's say, neural network. This is scalable, but it still requires the original expert controller. So you need to have the physics-based model in place, and you need to have lots of data. And very often it's hard to satisfy the guarantees of constraint satisfaction and stability as you would have here while solving the problem in real time. Okay, how do we alleviate the first problem of requiring accurate system dynamics model? Well, we can do reinforcement learning when we have some system that can be real physical system or computational, and we just observe the response on the perturbation on the control action that can be reward, and the next state we train the critic, which can be approximated by black box neural network, take the gradients of it to obtain the policy gradients for the actor, again, neural network. This needs to satisfy the Bellman equation, and there is a lot of research on doing reinforcement learning that is, again, offline optimization that will give you explicit control policy that solves the optimal control problem without requiring any assumption of your system dynamics model. Unfortunately, very often it's difficult to satisfy constraints and stability requirements when you don't have the prior knowledge. Therefore, we believe that the right way to go is to combine the prior knowledge from classical optimization with flexibility of machine learning, and differentiable programming is emerging as potentially unifying approach for data-driven parametric optimization that leverages automatic differentiation that could bring us there. So just to quickly review the recent advances in differentiable programming in the last 3 years, there has been amazing work from various groups. It's like differential programming is taking scientific machine learning by storm. Probably the term was coined by Julia people in 2019 in their overview paper. They call differential programming system to bridge machine learning and scientific computing. Very good read. Very famous paper on physics-informed neural networks, where you are using neural networks to obtain solutions for PDEs by minimizing the residuals of the PDE equations. Neural differential equations, again, they are being used everywhere from system identification in normalizing flows for approximating distributions. A lot of work is starting to be done in differentiable optimization. Instead of having standalone optimization solvers, now we can embed them as layers in deep neural networks and compute the gradients of the constraint optimization itself. Or we can learn neural networks to solve optimization problems and then use some differentiable methods like projections to obtain hard constraint satisfaction. And these ideas have been also adopted in control, where people are looking at differentiating model predictive control optimization problems. We are basically building on top of these prior works, leveraging some of the insights and ideas from different angles. What we do in terms of the overall abstraction, we would call it parametric optimization, because we want to solve explicit solution to some constraints given some nonlinear objective with automatic differentiation. So how can we do that? Here I want to present some idea that can be considered as generalization of physics-informed neural networks. Let's have this abstract problem formulation with nonlinear objective with our primal decisions x. That's the solution which we want to obtain. And with some of the parameter psi, which we can think as a collocation points in physics-informed neural networks. We could think of them as initial or boundary conditions in control problems. And we have set of equality and equality constraints imposed on the decision space. That could be either action space in control problem, or it can be state space in system identification problem of neural differential equations. And the solution map is a mapping of these parameters in these primal optimizers. It can be any function that is differentiable, but most often we will use neural networks that are parameterized by some parameters theta, and these are our optimization variables in this parametric optimization problem. To solve this analytically, it's infeasible for large problems, but we could solve this numerically with approximating the problem in Lagrangian reformulation. How do we do that? The most straightforward way is to put penalties on the top of these constraints, simple 2 norms or L norms, and they are weighted by some kind of weighting factor, which gives them relative importance with respect to the primary objective. By the way, if there are any questions, please stop me.
You described this as a generalization of pins. Is the top, I mean, when you take the Lagrange dual and you solve the bottom, most people think of pins as you just tack on a regularization term. So the top's not a generalization. The top's
no.
It's a specialization to the Lagrange dual on the bottom. That's the generalization. Is that right?
Yes. Yeah.
Okay.
Generalization is like, from my perspective, is you would do this residual only for PDEs, but doesn't necessarily need to be PDE equation. It can be equality constraints, inequality constraints in any constraint optimization problem.
Right, but the pin people would say just tack on that regularization, which is what ML people do. You can ask differentiable optimization questions up above with a projection or a prox operator or something and try and solve the hard constraint thing directly. So it's only the bottom half is the generalization of pins. You could do differentiable stuff on the top half.
That's
Right?
correct.
Okay.
That's correct. Yeah, exactly. And what it allows us to do, like this reformulation in Lagrangian form, now we can solve this with the gradient-based optimization because we have scalar valued objective function that you sample over your collocation points or parametric scenarios, and you are in the space of like machine learning. You can implement this in Julia, in PyTorch, and it can be a straightforward way to do things. In our team, we have been adopting PyTorch because there's a large community behind, and we figured out that there is a lack of tools in this space. So we start developing our own toolbox, which we call neuromodules, with adaptive nonlinear constraints and efficient regularization that allows you to formulate these high-level constraint optimization problems, and automatically it will transform them in these Lagrangian reformulations. If you are familiar with constraint optimization frameworks that are parsing the problem into the specific form that is required by solver, like interior point or active sets, this is something similar. It's just reformulation in the form that is suitable for stochastic gradient descent over collocation points. The APIs are very similar in the concept to optimization frameworks like JUMP in Julia, CVXPy, or PyMO in Python. You're starting with variable, that is your primary abstraction, and on the top of which you are building computational graph. You can have some neural network that is mapping some variable into another variable. So it's not only like mapping tensors to tensors. Now we have some symbolic representation of those tensors. And in our case, we implemented this operator overload approach where we can define arbitrary nonlinear functions. We can instantiate the objective functions through developed methods, and the comparative operators defines your constraints, like these inequalities, and you aggregate everything together in your objectives, in your constraints, and you add what we call here components, are trainable solution maps, neural networks that are going to change their parameters during the optimization in order to satisfy these constraints and minimize the objective. And how do you aggregate them all together in the Lagrangian reformulation depends on what type of approach you use. Penalty methods are the simplest one. You can use augmented Lagrangian and like all other methods like projections that have been mentioned in this line, and then you plug it in for a constraint optimization problem that is PyTorch module and has a differentiable forward path, and you can backpropagate and train. You can think of it as an architecture, neural network architecture with stochastic gradient descent over given sample data set of collocation points.
What does you mentioned SGD?
Mm-hmm.
You could is it peculiar to SGD, or you could do second order with a Newton type step or a sequential quadratic programming for constrained second order. Does that
Yes.
work, or does that not work?
Well, you could do that. We don't have it implemented yet, but in principle, the idea is that it should work. There are a lot of things that could be done. We are kind of in a prototyping stage, so we have long to-do list of features we want to implement, and we are getting there. For instance, interior point type solvers could be very suitable, but they are quite expensive. So how do you do this trade-off of having iterative solvers as a layer, but at the same time not sacrificing the speed of just having first order stochastic gradient descent? So,
and first orders sufficient for you, or do you need lots of hyperparameters like CV and an LP? And so
yes,
on?
you need a lot of hyperparameter tuning for complex problems that have a lot of constraints and a lot of objective terms. So that becomes a little bit tricky, and then you need to do hyperparameter sweep or some evolutionary algorithms to get you to those parameters. You also tried a bunch of experiments with augmented Lagrangian, where we have automatic updates of our duals, but we found that that's also pretty sensitive to hyperparameter setup. We don't have an answer yet, like that would work for everything. We are treating the problems based on their application. And if we know something about the domain, we can impose specific hyperparameters as a good prior guess. We can also impose some good initial guess on the solution map. It doesn't need to be instantiated as a black box neural network. So that's the direction which we are taking, rather like focus on a specific problem and leverage what you know about it, rather than finding the solution for everything. Yeah, but there are a lot of interesting works in this space that could deal, let's say, like with hard constraint guarantees through projections, which I'm not talking about here, but they're still in the same category. Yeah, so this is more like the overview of our approach. I want to move forward. How do we think about these individual components as a computational graphs? So this mathematical formulation can be reformulated as a computational graph when we consider some data set of sampled collocation points or parameters. You do forward pass through, let's say, neural network, and then you have some objects, your constraints and objectives that are all differentiable, and then you aggregate them in a loss function, scalar value loss function, compute the sensitivities, and you don't need to do imitation learning. That's the advantage of having these differentiable constraints, that you don't need to solve the constraint optimization solver prior, do imitation learning, and then evaluate the constraint satisfaction. Now the penalties will push you towards the feasible region. In our experiments, we can pretty robustly solve smaller to medium scale constraint optimization problems with non-convex feasible domains and non-convex objective functions, where here the green is a solution for interior point, the red one is the solution from this differentiable architecture. And in our experience, when you have the weight factors designed properly, the penalties will push you to the feasible region. Empirically, very robustly. You don't have any theoretical guarantees for that, but for many cases, just simple penalty functions will work very well. We don't have explanation why or when they break. Then going a little bit back. So then when you go level down, these computational graphs of neural networks, they don't need to be like fully connected deep neural net layers. You can put, again, some prior knowledge and architecture in there if you know something about our system. For dynamic systems, we have been playing with different architectures, what people call neural state space models. They are inspired by classical state space model in control theory. If you solve these problems in iterative solvers, then you have neural differential equations. But basically, each block here represents some nonlinear map. The orange one can be neural network, and blue one is linear map. And by arranging these different transformations, you can get this canonical representation of the dynamic system approximators, like the Koopman operators, where you have neural network observables and projections, Hammerstein meaner. So there's a lot of prior knowledge you could embed. And even on a lower level, in each of those black box components that can be represented by neural networks, you can embed prior knowledge from linear algebra. You don't need to train your weight matrices as a black box matrices. You can factorize them to, let's say, satisfy eigenvalue distributions. Here are two examples of linear factorizations which we implemented an open source on this GitHub repository, which we call structured linear maps. This one is a spectral decomposition when you have a left and right orthogonal matrix and you have diagonal singular value matrix. You clamp the singular values in certain region and you put penalties on orthogonality, or you use some transformations to guarantee orthogonality by design. These have been very useful for systems we know some dynamical properties, like in buildings. Here is an example of a real office building in our Richland campus in Washington, which is multi-zone office building, is fully occupied, and we have measurements of time series data of the temperatures in the zones. And the objective is to obtain dynamic system model that can predict the temperatures a couple of days ahead. So we can use it.
Can I ask a quick question about the previous slide?
Oh, yes.
That's good. Sorry, can you say this again? So how do you enforce constraints on the eigenvalues here?
So there are different ways. This spectrum map is nothing else as a singular value decomposition of your matrix, but you are not solving SVD. That would be very expensive. What you are doing, you are clamping your singular values in a certain region. You can do it with like few tricks, like using some sigmoid activation, and your left and right orthogonal matrices, you can put penalties to satisfy orthogonality property in the forward pass, and you add those as a regularization terms during training.
Okay.
Or there are tricks there. You can just design trainable orthogonal matrices through householder reflectors. There are some papers I can share that are dealing with just linear algebra factorization of the layers.
Okay.
They basically represent some inductive biases that they limit the space of the functions you can actually learn. So you are going away from universal approximator to more like specific approximators. Yeah.
Okay, that's very interesting. Thanks.
Yeah, thank you very much. So we have been using these priors in systems where we know something. Like in building, we know it's dissipative, which means that you will always get to the thermal equilibrium with the environment, which we know is dynamically stable. So we can leverage these spectral constraints and have stable convergent neural networks representing the system. And also linking to the slide before, instead of having black box neural network getting us to the solution of this constraint optimization problem, we can structure the solution that resembles the topology of the real physical system. Where in a physics-based model, you would decompose the problem to the building envelope, which are walls, ceilings, and basically represent the heat transfer within the structure. Then you have these heating, ventilation, and air conditioning components, like all the pumps and valves and radiators that are providing the heat into the building. And you are affected by disturbances like occupancy. People are switching on and off appliances, opening the windows, generating heat themselves, and the weather. So you have computational graph. Each of them is represented by dynamic system or algebraic system with different mathematical properties. And we impose these high-level constraints on the neural network approximation. So this is this basic structured recurrent neural net that gives you this recurrent update on the state trajectories that represent the latent temperatures in the building. And we know the dynamics is dissipative. That's why we put these eigenvalue constraints to be strictly stable within the unit circle. So it's always contracting and getting to the thermal equilibria. We know that our HVAC system has bounded input, bounded output properties, and we know what are the physical bounds. So we just can clamp the output of this neural network to be within these physical constraints. And we train only the fewer number of parameters as we would need to do with fully connected neural networks, because now our solution space is like fairly limited. Here I show example, like this is a very messy time series plot. You have 20 zones, 20 variables that represent temperatures in each of the building. And the red temperature is the ground truth measurements from the real building. And we have 30-day data set. The first 10 days have been used for training, second 10 days for validation, selecting the best model, and the last 10 days for testing, for comparing the prediction in blue with ground truth red. And these are the predictions of the linear model. What you can see is that, okay, linear models are okay for local predictions. You can learn linear model that is locally accurate, but after some time it will drift and you would need to retrain it again and do adaptive learning on the fly. When we compare with this neural model with physics-based constraints, we have found out that we can constrain the outputs and properties of the dynamics such that it doesn't blow away, doesn't escape the state space region that is supposed to be. And in fact, it gives us more reliable predictions and better robustness on the long term. So these are the experiments we have, which we have some with the real data from buildings. Now the question is, when we have the dynamical system that can represent our engineering system accurately, what do we do for control? Now the idea is, again, coming back to the same principles. Let's construct differentiable representation of the problem that we can solve with autograph and potentially like with stochastic gradient descent. The idea is, let's have a system model, couple it with control policy that can be approximated by neural network. And we have control parameters or features that are these collocation points, which we can forward propagate through the computational graph. And we have control objective function, which you can think of model-based value function in reinforcement learning. In reinforcement learning, you are mapping your state and actions into your rewards through reward signal. Here we don't assume any reward signal because we know what we want to do. If we want to track some reference, we can write parametric equation for that. If you want to constrain some data set of your collocation points, you propagate it through your state estimator. If you have partial observable system, you feed it to the control policy that generates the control action. The control action perturbs the system dynamics model. That can be either state space model, neural OD, or any differential equation. And now you have a response of the system dynamics model, on top of which you can impose constraints and objectives like reference tracking or stabilize towards the origin. And similar penalties of constraint penalties you can impose on control actions. And you aggregate all of those signals in the scalar value loss function through penalty or augmented Lagrangian. And now you can obtain direct policy gradients just by backpropagation or applying the chain rule. This exactly the same idea as for constraint optimization problem. Now we have optimal control problem with the dynamical system. Is nothing else, just rolling out the system dynamics. How does that work during training? What we found out, the convergence, if the model is like well posed, if the problem is having the right balancing of your objective terms, can be very fast. Here we are showing the policy landscape evolution and the closed-loop trajectories of this hello world problem that converge within 100 epochs. You stabilize towards origin and you satisfy those constraints. And you require fewer parameters than when you would need to have approximation of value function itself as well. Okay, so that's for deterministic system. Then we have been expanding this to include some uncertainties. Idea is simple, just orthogonally sample some perturbations of the system dynamics that can be additive or can be perturbing some parameters of the system dynamics model, and train it offline again. This is a little bit more expensive for offline case because of more samples that they require during training, but then upon deployment, you can be way more robust and satisfy the stabilization task or like this obstacle avoidance with parametric obstacle subject to perturbations. Second idea, which we explored in the space of stability and safety of these controllers, is okay, we can add Lyapunov functions during training and penalize the violations of the Lyapunov condition of the closed loop dynamical system. So Lyapunov function is nothing else as a scalar valued energy function that has a trivial null space, and it's positive definite. So it's like if you are following the energy landscape, it will always stabilize you at some fixed point, and that's very often what we want in closed loop control systems. We don't want our trajectories to run away. In this paper, we have been enforcing the stability, not only just penalties and constraints, but also by learning this Lyapunov function for the specific dynamics. So it's a kind of trade-off between having flexible controller, but still satisfying some convergence properties. And you can always use these as correction layers and do projections based on these energy functions upon deployment. And very similar idea is to use control boundary functions, which evaluate violations of your constraints around certain boundary of those constraints. And then you have some, again, derivative condition that needs to be satisfied in the interior of the feasible region. And as you are progressing towards your constraints, it's tend to be violated, and then you trigger your safety controller, which can be projection again on feasible set by solving some QP. So these are different ideas that can be combined with just purely differentiating your constraints and adding penalty functions. There are way more methods that other groups have been working on, with also embedding iterative solvers itself, like this differentiable optimization layers. It's one example. Okay, so these are theoretical and methodological approaches. For some practical applications, we have been trying to test those on control problems in building energy optimization. Here we have 6-zone building, residential building, which we want to satisfy the temperatures within certain constraints, time varying constraints, and manipulate the actuators like the mass flows and supply temperatures to optimize the energy use and balance with the comfort. This is fairly complicated parametric optimal control problem, and we have been having some success of scaling it up to system, the emulator system underlying model of the real building that had 300 states. So these are fairly large systems with continuous state and action spaces. And the methodology was first system identification with constrained system dynamic model, plug the learned surrogate model in the closed loop, and differentiate the closed loop dynamic system with respect to MPC type objective. And exactly the same architecture with just different prior on the system dynamics has been used to solve dynamic economic dispatch problem, where you have power system network, you have generators and consumers, and you want to balance out the network while satisfying some frequency constraints. You want to keep things stable. Here again, we obtain time series of the power system network, learn the Koopman operator, plug it in the differentiable closed loop system, and obtain the sensitivities through automatic differentiation for the policy optimization. In this particular case, we obtained 5 orders of magnitude speed up compared to interior point, which was very encouraging even for this small case system. And we are currently on the lookout for scaling up the problems to larger state spaces. So I'm going to just skim through all of these and finish with the implementation of this procedure to embedded hardware, where we demonstrated the concept of software or control as a service. This was done in collaboration with our colleagues in Europe, in Slovak University of Technology. They have this very simple laboratory device, basically floating ball in the tube, that is controlled by a Raspberry Pi controller that has limited compute and memory. They designed model predictive controller and PID controller, and they shipped us time series data of the measurements of the behavior of the system. We did system identification. We used the learned system model In the closed loop, we train the control policy using these differential predictive control principles, and we ship them the control policy, never seeing the system, and they deploy it on Raspberry Pi and compare against MPC and PID. The results have been quite favorable in a sense that model predictive control is quite expensive. That's why they had to do some reductions in their problem complexity that hampered their performance. Because we pre-computed the solution offline and deploy only neural network, we didn't have to do these simplifications, and we obtained better performance in terms of the reference tracking. Here, the blue is the differentiable controller. The purple one here, that's the model predictive control that has some delays. And we have been also able to deal with the dynamic constraints and dynamic reference tracking while having perturbations from the system, like lots of noise. And what you can see, like the system, because it has been a constraint to satisfy the penalties, is avoiding the constraints in order to not to violate them, because it was trained with some distribution of the noise. Okay, so this was very exciting to see that we don't need to be there in person in order to make it work for real system. And I will wrap up with the conclusion of the work which we are doing in our team, which is primarily interested in using differentiable programming and combine with principles of constraint optimization to solve parametric optimization problems that range from solving constraint optimization with changing constraints or objective functions, system identification with changing boundary initial conditions, optimal control problems with different tasks. And that's why we see it as very generalizable approach, and a lot of research is being done in this space. Our ongoing work is to improve the constraint optimization solvers, potentially going to the second order ones, like has been mentioned today, embedding graph neural networks in a framework that can give us better structural priors for network dynamic system, like power systems or buildings, doing some robust uncertainty quantification with respect to parametric and additive uncertainties. And in long-term vision, we see like the community can bring a lot of ideas from classical numerical methods, physics-based modeling, and new trends in differential programming to do causal discovery, dynamical coupling, stability analysis of large machine learning models with provable certificates for safety. That would allow you to solve large-scale optimization and control problems. So here, I would like to thank you very much for your attention. I would like to thank Department of Energy for funding us, and I'm happy to take any potential questions.
Thank you a lot for your talk. Any questions?
I do have a questions. If usually, what's a typical data set size of the data set that you work with for this particular class of problems?
It depends heavily on the application space. If we are dealing with some small scale problems, we have been training dynamical system models, neural ODs with some domain priors on a couple of hundred of time steps. So when you have good prior, you can learn these models on small data. On the other hand, when you are solving optimal control problem with uncertainties, you need hundreds of times, thousands of samples, even for relatively small problems. So that really depends.
I see.
Mm-hmm. More uncertainty you have and larger parametric space you want to explore, the more collocation points you will need to have, more data you need to have.
Okay, thank you.
Thanks.
Thanks for the nice talk. I had a curiosity. I had a question about especially the context where you're verifying, where you can provide guarantees on the satisfaction of the constraints. and they're with models that are trained end to end. I mean, a lot has been done, but it's very dependent on the problem form. So do you have any insight on whether we can push the envelope to get to the resolution of more complex problems and constraints, namely non-convex, nonlinear optimizers?
Non-convex are hard. We have tried a bunch. You are asking for theoretical guarantees or some empirical success?
Well, empirically, yeah, I think we do have evidence that empirically things might work in certain domains, but
yes.
Then actually providing hard guarantees, that is the ultimate goal, right? So
yes.
in a sense, I wanted to get your perspective on that context as well.
So I don't have an answer for that, but I have some ideas for the directions. In our team, we are going case specific. Like when we know something about the system, it's easier to prove guarantees because you can put these domain priors and design the problem architecturally that will have bounded parametric space and the output space of the approximation network. For more generic directions, we have been recently exploring homotopy methods for non-convex problems that has been studied in power system networks, where the idea is very, very simple. Like you start with some convex relaxation of the problem. You solve that first to get to that proximity of your solution, and then you continuously transform to that non-convex problem. There are some works that provide some convergence guarantees in the context of power networks for constraint optimization problems, and we would like to explore it in the context of differentiable programming as well.
That seems very interesting.
Yeah.
Thank you.
Thank you.
Okay, if there are no more questions, then let me thank you again for this wonderful talk. And